Good afternoon or good morning, everybody. I'm Wengui from University of Technology, Sydney, Australia. Today, on behalf of this team, I would like to talk about multifunctional graphene cement-based sensors for structure health monitoring. This is outlined at the beginning. I will talk about cement-based sensors use graphene nanoplates, which is also called GNP and graphite plates GP. And then I will discuss the cement-based sensors exposed to sulfate acid attacks. And next, we will talk about the development of hydrophobic cement-based sensors use silicon powder. And finally, I will discuss the integrated self-sensing and the hydrophobic capacities using CNAM coating for graphene cement-based sensors. Okay, now at the beginning, as we know, concrete is the most widely construction materials for buildings, bridges, tunnels, and harbors, as well as pavement. Concrete is non-conductive. But when we add conductive materials, such as carbon and graphene materials, the concrete turns conductive, and the electric resistivity of concrete becomes much low. So actually, the conductive cementitious composite can act as cement-based sensors for structure health monitoring. And then when the loading, external loading, or the environmental actions, the electric resistivity of cement-based sensors changes due to the damages such as cracks and large deformations. So in this way, we can use cement-based sensors to evaluate the health condition of concrete infrastructures. So now, how can we evaluate the performance of cement-based sensors? Basically, we can use the changes in the electric resistivity of cement-based sensors when external load the environmental actions is applied to define the piezoresistivity of cement-based sensors. And then what factors influence the piezoresistivity of cement-based sensors? And basically, the factors include raw materials such as conductive materials, the manufacturing process, environmental actions, external loads, as well as measurement methods. So now I start to talk about cement-based sensors use GNP and GP. As you can see, this is the procedure to prepare cement-based sensors. Before the mixing, both GNP and GP are added to solution and then treated by stirring and ultrasonication treatment. After that, we add both GNP and GP solution to cementitious composite. And then, as you can see, on that hand, as you can see, both the compressive strengths and fracture strengths of the at different content of GNP and GP. At the beginning, with the increase of the content of GNP and GP, both strengths increase, but then decrease when the content of GNP and GP arrived at a large amount. In the real test, both GNP and GP are used by different concentrations by weight of the binder. As you can see, based on these images, both GNP and GP have small sheet size, right? And then, but the GNP present large size and the sink near compared to the GP. Additionally, both material have excellent electric conductivity and with resistivity as low as 0.001 ohm centimeter, as you can see from here. Now let's look at the observance of GNP and GP solutions. As you can see from here, at the beginning, both GNP and GP solutions exhibited constant absorbance values regardless of the dispersion methods. But these absorbance values change with time, and because of the GNP and GP particle segregation. Additionally, as we can see from these figures, the GNP dispersion is much better than the GP and the same treatment. It means the dispersion efficiency of GNP is better than the GP and the same treatment. So now let's look at the electric resistivity of GNP and GP cement paste. As we can see from here, when the content of GNP and GP is below 1%, and then we can see the resistivity of GNP and GP is quite similar to each other, which is around 10 power by 7 ohm centimeter. But for the resistivity with GNP, experience a sharp reduction until to 10 power by 6 when the GNP content increased to 2%. On the other hand, we can also find from this figure is that the GNP cement-based sensors has higher electric conductivity and also exhibited better piezoresistive sensitivities. So now let's talk about the duration of ground-phase cement-based sensors after exposed to sulfuric acid attacks. As you can see, this is the surface appearances of the specimen after exposures to acid solution for 90 and 180 days. Basically, we can see the deterioration rate of the ground-phase cement-based sensors increase with the immersion time and also the increased acid concentration of the solution. So now here, let's look at the mass change compressive strength after exposed to acid solution. So firstly, we can see the mass growth increases with the increased acid concentration and immersion time. And similarly, the compressive strength decreases with the increased acid content and also the immersion time, as you can see from here. So now let's look at the fractional change of resistivity exposed to sulfuric acid attacks. After 180 days immersion. So firstly, we can see the piezoresistive linearity and repeatability becomes poor. This is due to the damage of the conductive networks and the damage of the microstructures of the specimen. So in this way, we can see the piezoresistivity performance of the ground-phase cement-based sensors is affected by the highly corrosion environment, as you can see from this image. Now let's talk about the electric resistivity changes of the specimen. Firstly, as we can see from this figure, all the specimens experienced a reduction in the resistivity under compression, and then when the stress reaches to the ultimate compressive strength, and then we can see there is a sharp increase. There is a sharp increase in the resistivity, and this is because the damage destroys the conductive pastures in the specimen. On the other hand, we can find the largest change of the fracture change of resistivity, which is called FCR, when the specimen is immersed in 3% of the acid solution. So now here we are going to talk about the hydrophobic cement-based sensors using GNP and the selenium hydrophobic powder, which is called SHB. As we can see the microstructure and the morphology of SHB in this image. And then let's look on that hand, let's look at the compressive strengths with various content of SHP and GNP. For the plain cement paste and the specimen with 1% SHP, we found that the compressive strengths increased with the GNP content. And on that, but for the specimen with 2% SHP, then the strength decreases when the content of the GNP increased to 2%. So now here we talk about the water absorption as a function of time with various content of GNP and SHP. Firstly, we can see SHP can clearly improve the water impermeability by decreasing the water absorption, right? And then we also found the best water impermeability happened for the specimen with 1% GNP, but the impermeability was slightly decreased when the content of GNP increased to 2%, and this may be due to agglomeration of the GNP particles. All right, so now let's look at the fracture change of the resistivity of the hydrophobic cement-based sensors with or without SHP after or before water immersion. Firstly, without SHP after water immersion, we found that FCR presented a different patterns by a high increase in the resistivity because of the water penetration into the cement-based sensors. On that hand, with 1% SHP, the FCR afterward immersion was generally identical to the original values, except for the alterations at the beginning of the compression. So now here I would like to explain why the piezoresistivity with SHP is not affected by the water immersion. The reason is that the SHP actually helps to establish the hydrophobic films on the surface of the specimen. And then the hydrophobic films on the surface of the pores and voids can achieve the hydrophobic capacity for the cement-based sensors, as you can see from this figure. So now here I'm going to talk about the integrated, talk about the ground phase cement-based sensors with integrated self-sensing and the super hydrophobic capacities. And here you can see how the cement-based sensors are prepared in the laboratory. And then here I would like to talk about the CNM coating procedures for cement-based sensors. Basically, there are three types of surface coatings, including once coating, twice coating, and once coating without isopropyl, as you can see from here. Now let's look at the surface wall contact angle of the cement-based sensors used after or before sealant coating treatment. Firstly, we can see all the coated cement-based sensors showed hydrophobic capacity with contact angle larger than 120 degrees. In particular, the twice coated sample exhibited the largest value up to 160 degrees. So now we first look at the water contact angle of the cutting cross section area of the specimen, and then we can see the sample without CNM coating treatment, and then the water contact angle is around 70 degrees. On that hand, after CNM coating treatment, we found that the contact angle is up to 140 degrees. Here I would like to introduce the FCR, which is a fractional change of resistivity of cement-based sensors after with or without CNM coating treatment. Firstly, we can say after CNAM coating treatment, all the FCRs exhibited excellent relationship to the compressive stresses with reversible resistivity during both loading and unloading processes. And then additionally, it also indicates the cement coating doesn't affect the piezoresistivity of the cement-based sensors. Now here I would like to explain the mechanism of super hydrophobic mechanism. Based by the physical intrusion and chemical reactions. So to achieve the super hydrophobic capacity, the intruded CNAM actually have chemical reactions with cement matrix and then produce equivalent bonding between cement and CNAM. Now here we come to the conclusions. Firstly, we can see both the GNP cement composite and GP cement composite exhibit conductivity and piezoresistivity when under external loading and environmental actions. And secondly, after sulfuric acid attacks, the piezoresistivity becomes less linearity and repeatability. And thirdly, with addition of the SHB, and we can see the hydrophobic films can mitigate the effect of water immersion on the piezoresistivity performances. And finally, the hydrophobic CNAM treatment CNAM solution can penetrate into the cement-based sensors after coating treatment to reduce the water absorption of the hydrophobic cement-based sensors by half further. Okay, now this is the end. Thank you very much for your attention. Thank you.
All right, Dr. Lee, I think there's already one question in the chat box by Maria. How was the conductivity measured? Was AC or DC?
Yes, we use, actually, we tried both DC and AC. So I think we used the DC at the beginning, use the DC to match the conductivity in the real test. We use the DC for the measurement.
Okay, so it's bulk resistivity, right?
Yes.
All right.
Yes, actually, we used, at the beginning, we used the 2 electrodes, and then further we improved, we also used the 4, this is 2 electrodes, right? And then later we used the 4 electrodes to match the resistivity of the specimen. And
right.
like here, this is the 4.
So I have a follow-up question on this one. How sensitive was the measure, the resistivity measurement to the ambient relative humidity?
I think yes, it's we can say it's sensitive to the community of the environment. Actually, here when we, for example, when we put the sample in dry condition and the environmental with high humidity, we can see the value changes greatly. So I think it is very sensitive. Get another question. Oh, Mary. Okay, thank you.